All right, well, in the interest of getting things started, I'm going to go ahead and stop sharing. And Allison, you can go ahead and feel free to start sharing anytime you like. And I'm meanwhile going to make some announcements, and then we'll do the introduction and get going. And I'm sure people will begin to roll in as we do this, okay? All right, so first of all, it looks good. Yep, full screen and all good. Okay. So welcome back, everybody, to the SMU Physics Department Speaker Series for Spring 2021. We're continuing the March series today, again, with its theme of New Frontiers in Physics after taking a brief pause last week on March 8th when we didn't actually have a seminar. Let me note that in a moment, I'll go ahead and introduce today's speaker, but I want to start with just some comments at the beginning. So first of all, many of our March talks showcase research that's ongoing in our own department, and faculty from a variety of subjects will be presenting their work. And this week is one of those weeks. And the aim here is especially to highlight faculty who are interested in attracting students to their work. Now, some final usual reminders. First of all, to our audience on Zoom, to ask a question, go ahead and type speak or something equivalent to that in the chat window. That'll let us know that you want to talk, and then we'll get you unmuted because we have the mics kind of locked down because we're live streaming for all of this. But we can unmute you, and then we can start a dialogue between you and the speaker at that point. You'll only be able to speak when called upon and asked to unmute by a moderator. And hello to our friends and colleagues on the YouTube live stream. We're also streaming simultaneously on YouTube as always. So without further ado, let me go ahead and introduce today's speaker. So I am very pleased to welcome Professor Allison Deiana today to speak. She earned her undergraduate degree in physics at North Carolina State University before pursuing and earning a PhD in physics at the University of Illinois, Urbana-Champaign. After conducting postdoctoral work at the University of Michigan, she joined the faculty at SMU in 2018. Her research program is focused on the ATLAS experiment at the Large Hadron Collider, where she pursues physics topics related to searches for new particles and also the study of the Higgs particle discovered in 2012. She's been a leader in the beyond the standard model Higgs physics community within the ATLAS experiment and beyond, and now focuses her work specifically on Higgs interactions. She and her group are in pursuit of a measurement called the Higgs self-interaction, which she'll talk about today. And that's where she investigates the subject through sort of two areas, the production of two Higgs particles in a single proton collision, or Di-Higgs physics, as well as single Higgs production in a proton-proton collision, but where it's accompanied by at least one top quark. Her group is also focused on developing firmware needed for upgrades to the ATLAS liquid argon calorimeter. And today she will talk about the latest results in one of the Di-Higgs searches, where one Higgs decays to a pair of bottom quarks and the other to a pair of tau leptons. So welcome, Dr. Deiana, and you can go ahead and get started anytime you like.
Okay, thanks. So just one quick question is, can you see my mouse on the screen?
Yes, indeed.
Okay, so I can use that as a pointer.
Perfect.
All right, so as Steve said, today I'm going to talk about searching for new physics through Higgs boson pair production, specifically where one Higgs goes to two bottom quarks and one goes to two tau leptons. So to start off, okay, I do have control. It's just lagging. There we go. To start off, as he mentioned, I am working with the ATLAS detector at the Large Hadron Collider. So a lot of people at SMU are familiar with this, but I wanted to give a brief introduction of what's going on. What is the LHC? What is the ATLAS detector? So the Large Hadron Collider is a proton-proton collider that's circular. You can see it has a 27-kilometer circumference. Here it is overlaid on the Swiss and French countryside. It's underground, actually, so it's not just sitting right there. It's like 100 meters underground in a tunnel. And at several points around this ring, protons are made to collide inside of detectors. And the detectors that are recording these collisions are the CMS detector and the ATLAS detector, and then also LHCb and ALICE. So today I'm talking about the ATLAS detector, which is right here. And it's a general purpose detector. So what that means is it's designed to try and be able to detect as many different sorts of particles as possible. Most notably, it cannot detect neutrinos. So those we infer by through energy conservation. And this is a little diagram of the ATLAS detector right here, where to show the scale, you can see the little humans right here on the spindle. So it is a truly massive detector that is now sitting underground in a cavern just here. Okay, so in another note is the data that we have collected over the years. this graph right here is basically showing like how much data we've collected as a function of time for each year. And you can see that it's the curve of how much data we're collecting over time is getting sharper and sharper as time progresses. So here down here, you can see 2011, we were gathering data at a relatively low rate, so the low slope. And then as we get further and further, here's 2012, and then 2015 and 2016, and then now to 2018, that's the most recent year of running. You can see we have a very sharp curve for data that we have collected over time. And that's measured in terms of delivered integrated luminosity. Okay, so now all of the results I'm going to show today are conducted using proton-particle collisions that were collided at a center of mass energy of 13 TeV, which corresponds to years 2015 to 2018, and a lot of them only include years 2015 and 2016 so far. So there's a lot of work still ongoing for the later high data quantity years. Okay, so before we got into the analysis parts, I wanted to say a little bit of what exactly the Atlas detector is made of and how it works. So this is like a pie slice of a cross section of that cylindrical looking Atlas detector. So what you can see in here at the very center here is the interaction point where you would have the two protons colliding. And then surrounding it is a tracker. So basically what we see here is where the charged particles pass through, we can reconstruct a track, and based on that we can find the transverse momentum. And then outside of this tracking detector, we have two separate calorimeters. And so the calorimeters, you can see, interact with the particles and creates these showers of subsequent particles that are absorbed into the calorimeter, and the energy is measured. And so this is how we measure particles like photons that would just pass through the tracker here, and protons, the quarks that make up protons, and neutrons, and so on. And then outside of the calorimeters, we have what's known as the muon spectrometer. And so this is useful because muons actually just pass right through the detector. We see them in the inner detector, and then we see them also in the muon spectrometer out here because they do not interact with the calorimeters. So then we can match a track that we see out here with one we see in here and find our muons. And then this dash track shows just the neutrinos, they're invisible. Okay, so this is kind of a quick crash course in like the basic systems of the Atlas detector and how they work. So now I wanted to get into what we're looking for the Higgs boson and why. So to kick that off, I want to mention what is the standard model, what is the Higgs boson in the standard model? So the standard model of particle physics is basically the framework through which we understand how particles interact with each other as of now. So far, we have not found any clear deviations from the standard model. And one of the things that was predicted by the standard model, which was not observed before the LHC program, was the Higgs boson. And so its discovery in 2012 was a major success of the LHC program. So far, in all observed production modes, the Higgs boson is consistent with expectation. So that's what I'm showing here on the left-hand side here. This is one of the summary plots of the cross sections measured for a variety of different production modes for the single Higgs boson. And you can see this one right here corresponds to what you would expect with the standard model of particle physics. And you can see that all of these results, though they kind of fluctuate up and down a little bit, they are all consistent with the standard model. And these different production modes are gluon fusion, vector boson fusion, and associated boson production, and top associated production. Okay, and in terms of how frequent these different kinds of collisions would happen at the Large Hadron Collider, you can see that from looking at the size of the cross-section right here. Where basically for a given amount of data that we collect, if we have a larger cross-section, that means we're going to have more events of a particular type than a different type of process that has a smaller cross-section. So here you can see this is the gluon fusion cross-section here at the top. That's the highest cross-section. That one you can see we have measured. Vector boson fusion, associated boson, and top associated production here. And then way down here we have Di-Higgs production. So this is actually gluon fusion Di-Higgs production. So we have observed all the way down to this dotted blue line, but we have not actually measured yet this dotted gray line, the Di-Higgs production. So that's one of the things that we're targeting right now. So just to say a little bit about where Di-Higgs Higgs pair production comes from, we can look at the Higgs potential in the Standard Model. So this is basically the Higgs potential in the Standard Model, the part of it that's relevant for us right now. We can expand this potential about the minimum value, which is the vacuum excitation value here, and get an expansion that looks like this, where we have terms that are related to the Higgs field squared and cubed, cubed, and to the fourth. And basically what this corresponds to here is the Higgs mass term in the squared part, and then we have a trilinear self-coupling term right here, and we have a quartic term right here. So this trilinear self-coupling term is very hard to measure and hasn't been done yet, but it is potentially reachable with the LHC program. This quartic term is not really reachable, so it's not something that we're focusing on right now. So this is what we're talking about right now, is the trilinear self-coupling term, where you have basically a vertex here with 3 Higgs bosons. Okay, so to talk about the process specifically that we're looking for, most of the searches for Di-Higgs right now are targeting gluon fusion, and that's because that's the largest Standard Model production mode. The Di-Higgs production modes kind of follow the same hierarchy as the single Higgs production modes, in that the gluon fusion is the highest, then you've got VBF, and then the boson associated, and so on. There is such a thing as top associated Di-Higgs production, but it's very, very small for our section, so that's not something we're focusing on right now. Okay, so these are an example of the diagrams that contribute to the process. That these involve top and bottom quark loops. As you can see here in the left-hand side, this is a top or bottom quark loop that produces 2 Higgs bosons, and we call that the box diagram for obvious reasons. There's a box there. And then on the right-hand side, which you can see is the triangle diagram, as we sometimes call it. This is the diagram that involves the trilinear Higgs self-coupling, which you can see right here in this vertex. And so we kind of refer to that coupling with a lambda HHH. Okay, so this is what we're focusing on. And so clearly to see this self-coupling, we need to be able to kind of disentangle these two effects, the effects that come from the 2 different diagrams. And in fact, this is actually fairly complicated to do. As it happens, the Standard Model cross-section is dominated by this box diagram with a small contribution from what I was calling the triangle diagram. So you can see the box diagram here in blue as a function of the mass of the HH system, and the triangle diagram here in red. And between the two, there's actually also a massive destructive interference term. So when you add all of those together, you get a sum cross-section that's actually considerably smaller than what you would expect from even just the box diagram. And as it happens, the cross-section is therefore about 31 femtobarns in the Standard Model. So this complicated picture adds some kind of interesting aspect to the analysis, because the value of this trilinear Higgs self-coupling doesn't just affect the overall amount of Di-Higgs events that we'd expect to find at the LHC. It also affects the kinematics of the events, and by affecting the relative contribution that you would expect to see from this triangle diagram and this box diagram. So you can see if you have a larger contribution from the triangle diagram, then you're going to be more dominated like at the low MHH spectrum here. So that's something that we take into account when we're looking for new physics as well. All right, so therefore, we then have 2 main things that we're looking for in these analyses. First, there is the overall Di-Higgs production cross-section. That includes the box and the triangle diagram. That includes everything, just anything that ends up in a Di-Higgs that decays to, in my case, BB tau tau. So this could be changed if we have new physics. There might be some new process that just ends up with a Di-Higgs in the end that we don't expect. And so then we would pick that up in our analysis, and then we would get a larger cross-section than we'd expect. It's also possible that there is something that is affecting the trilinear Higgs self-coupling. And through that, we could get an enhancement or a decrease in the overall production cross-section. And then the second thing that we look at is the self-coupling itself. So the modifications in the self-coupling itself can affect this overall Di-Higgs cross-section, but also it can affect the kinematics of the signal events. So we can narrow down on the trilinear Higgs boson self-coupling even separate from looking at the overall cross-section that is also dominated by the box diagram. And what you can see here on the right-hand side is basically how strongly this self-coupling can modify the kinematics of the events we're expecting. So here, this kappa lambda, which we defined as our measured lambda divided by the standard model lambda. So this kappa lambda 1, which is green, is actually the standard model value. You can see it peaks around MHH of 400. But if we were to say our kappa lambda is 10, you can see the peak looks very different. It's this light blue one, right? So then these are very different kinds of events that we're looking for. And then this -5 value, you can get this kind of peaky structure. And then like there are a few other examples here. They're just on 2 different plots. There's no deep reason for that. Where you can see if our kappa lambda were 0, so they're just 0 self-coupling, then we would get this black diagram, which is actually somewhat similar to the standard model case. And then here's 2 and here's 5. So you can see that there is a handle in the signal to be able to distinguish this self-coupling value even separate from the overall numbers of events we see. Okay, so that is the search for the self-coupling. There is also a separate way to look for new physics with Di-Higgs, and that is, what if there's some mediating particle here that we've never detected before that is maybe very massive and then it's decaying to Di-Higgs? So that mass could be anything. It could be like a graviton. It could be some unknown heavy additional Higgs boson. And we can look at higher and higher masses here and see if there's some particle we might not have seen in other searches that would decay preferentially or some sizable amount to HH. And so that's what we refer to as resonant searches, because this would be the resonance here at the X. Okay, so now that I've told you about what we're looking for exactly, let's get into the actual analysis. Okay, so this is a quick summary of how Atlas searches for Di-Higgs. You can see all of the possible final states here in the right-hand side, where the y-axis is the decay mode of one of the Higgs, and then the x-axis is the decay mode of the second Higgs. And the thing to note here is that your fraction of Higgs events that are going to particular final states is higher as you go up here and lower as you go down towards the blue. So we have more events going to BB, BB, than we do gamma, 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 for instance. So there's a trade-off to be had here when you're trying to decide where you're going to search. The trade-off is that if you look at BB, BB, then you have a very high amount of Di-Higgs events going to this final state, but at the same time you have very high backgrounds. If you have gamma, 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 then you have a very, very small number of signal events, but you also have very few backgrounds, I would imagine, in the 4 gamma event. So what I'm looking at is a BB tau tau, which sits right around here, as a pretty sizable branching fraction, and the taus give us a more unique kind of signature that we can separate from backgrounds. And this over here is just a summary of all of the papers if you want to look at all of the various channels that Atlas has searched for. You can see it's a very active field. There's a lot of papers from 2019 and 2020. And today I'm going to talk about BB tau tau resolved and boosted right here. And then also to note that many of the channels have been combined as well into a overall Di-Higgs combination. All right, so as we move into the analysis section, I will give a brief background on tau leptons. So I am looking for a case where we have a Higgs boson decaying to 2 taus, and that, as I said, can help us to distinguish from backgrounds. And the way it can do this is that the tau leptons, because they're very massive, they can decay actually into other leptons, or they can decay into jets. So if they decay into other leptons, then that is going to appear as an electron or a muon in our detector. And then electrons and muons, we are very good at distinguishing from other types of particles with the Atlas detector. And then if it decays to jets, then there are ways that we can distinguish hadronic decaying taus, as we call them, from just jets of hadrons. And you can see some of the differences here, for example, like that taus tend to have 1 or 3 tracks that are charged, and they tend to be very close together in kind of a cone and surrounded by an area of isolation of energy. And that's not necessarily true of jets of hadrons. And so for the overall final states of the di-tau system, you can see it's separated out into a pie chart here. So for our analysis, we consider the case where 2 taus are hadronic, or where one is hadronic and the other goes to an electron or a muon. And you can see that covers the vast majority of events in the tau-tau system. All right, so our search includes, as I mentioned, both what I called a resolved search and a boosted search. So let me tell you what that means real quick. For a resolved search, that means that we have these 4 objects, 2 bottom quarks and 2 taus, and they go out into the detector, and we're able to distinguish them all 4 separately. Then for the boosted search, what that means is that we have a much higher energy. Typically, it's some kind of resonance decaying to 2 Higgs. And because you have a much higher energy, it pushes these objects to be closer together. And eventually, they get close enough together that you cannot distinguish the 2 separate particles from the detector. So the 2 bottom quarks might be very close together, and we just see them as one massive blob in the detector. The 2 taus might be very close together. And then we can't separate them with our techniques that we have to figure out what our particles are. So in the resolved case, we're looking for non-resonant and resonant. In the boosted case, because it's specializing in like high energy events, we're looking only at the resonant case. So the boosted Di-Higgs to BB tau tau is the latest BB tau tau result. And it is now targeting some kind of a resonance that could have a mass from 1 to 3 TeV. So in that range, both of the decay products are going to get merged. So instead of looking at trying to find each of the 4 objects separately, we're looking for 2 large jets, one of which is B-like and one of which is tau-like, basically. And for the BB system, we're basically using kind of what is the standard method in Atlas, which is that we have a cone for our jet that has a very large radius, and we're looking to associate subjets within that cone that look like beach jets, basically. And for that tau-tau system, specifically for this analysis, we developed and commissioned a new reconstruction identification technique, which involves looking again at a large radius jet and trying to distinguish from what we see inside that jet whether there are objects that look like 2 taus or not. And I'll talk a little bit more about that. And this is physically what an event looks like in this boosted search in the detector. You can see these 2 big old cones here. One of them is the di-tau on this side, and this one over here is the di-B jet. We anticipate, assuming this is truly a BB tau-tau event. So this is what is identified as the di-tau, and this is identified as the BB bar. Okay. So for this tau reconstruction technique, we're looking for a large radius jet that has at least 2 smaller jets within it that have at least 1 associated track with them. And what these plots here are showing you is how the standard tau identification, which is looking for what we would call resolved taus in the detector, performs relative to this boosted di-tau ID. And what you can see in the left-hand plot, what is on the x-axis is basically for this 2 tau system, how close are the taus to each other in angular space? You can think of it that way. So like at 1, they're quite far away from each other, and then as they get closer to 0, the 2 taus are getting closer and closer together. And the standard kind of radius parameter that we use to look for taus is at 0.4. So what you see here is that as the taus get less than 0.4 away from each other, then our resolved tau ID just stops working because they're just too close together. We cannot split them apart. And what you can see here with the boosted di-tau is that it works really well, actually, in between like around 0.2 and 0.4. where we would be missing all of these events with our resolved reconstruction. And as you get to 0.4, the boosted does not outperform the resolved, and that's kind of expected as well. It's really designed to deal with this case where the taus are very close together in angular space. And then what you see on the right-hand side here is the efficiency, again, as a function of the PT of the di-tau system. So that also shows kind of what I was telling you before, that the boosted case is really for when we have very high energy events, really high energy objects in our event. So you can see that as the energy of the di-tau system increases, the boosted becomes better than the resolved case. Okay, and this is considering only the case where we're greater than 0.2, which is basically all of the events here. We can't do anything less than 0.2. Okay, so that's how we were dealing with reconstructing our di-tau system. And then past the reconstruction step, we have what we call identification, which is where we want to find the best efficiency that we can versus rejecting things that are not actually di-taus to try and separate our signal from our background. And for this, what we've been using is a BDT, and it's trained to select di-tau objects against multi-jet events. So those are mostly like QCD processes. And I'm not going to go through all of I do have them in backup if anyone's interested, but I'm not going to go through all of the BDT variables, but I can just tell you that the variables that are used include information about stuff like the clusters in the calorimeter, the tracks, where are the tracks, and vertices, like where's the primary vertex of the tracks, and is there a secondary vertex, that kind of thing. Okay, and what you can see here is the performance of this identification. So here on the y-axis, what you have is inverse background efficiency. So you want that to be high. So this is like a 1/10⁶ background efficiency here. And then on the x-axis is signal efficiency. So we want that to be reasonably high as well. And what was used in this analysis was a 60% signal efficiency, which corresponds to like basically a 1/10⁴ background efficiency. So you can see we're keeping way, way more di-tau events than background events in terms of efficiencies. Okay, so for calibrating it also, we use scale factors that correct the performance in simulation relative to data, and then we also measure uncertainties on those scale factors. And for that, we look at a control region that has one di-tau object, just like in our signal region that we're looking for. But then the object that we would say we're looking for our 2Bs in, we look to make sure that the subjets within that don't look anything like B-type jets. So that way it's completely separate from where we're looking for our signal, but it's still going to be enriched in events that have di-tau objects. And we measure a scale factor there by looking in data and basically comparing what we see in simulation to data. And this is what you can see in this plot right here, where this is our true di-tau from simulation. This is multi-jet events, the yellow, and this is just like all other processes combined because they contribute very small amounts. And we compare that to data, and we can get a calibrating scale factor when we fit this. Okay, and so then for the final signal region that we're looking for, you can see we don't have very many events in this boosted region. So this is the HH mass, which is what I was showing you before when we were talking about like the impact of kappa lambda. So it's the reconstructed mass of the HH system. Here we're requiring our di-tau object, we're requiring ourselves to have a large radius jet that has two BTAG-like things inside of it. And then there's also some cuts on the missing transverse energy and the distance between the di-tau system and the missing transverse energy. And then past that, we have some cuts depending on what mass we're looking at on our mass of our HH system. What you can see here is we actually only have 2 events in 139 inverse femtobarn of data. So you can see there's a pretty tight selection, 2 data events. And we expect to have about that many, honestly, given uncertainties. So there's no, unfortunately, sign of signal yet, but this is a very low stat analysis as of yet. Okay, so this is what our final limit looked like. And what I've marked here with the lines are where our cut on the MHH variable changes from 0 to 900 to 1200. So that's why there's discontinuities here. So you can see the performance of the boosted algorithm is not so great at 1 TeV, but then it improves. We get a much better limit as we get towards 1500. And then we start excluding more and more background events as we tighten the cut there. And do quite good at 2.5 to 3 TeV. So that was the final result for this analysis. So then the other approach to BB tau tau that I wanted to talk about today was the resolve search for BB tau tau. So this is covering a complementary range of resonance search from like 260 GeV to 1 TeV. And instead of using the mass as like the final thing that we look at, we are using a BDT score. So in this case, we're not using any of those new di-tau identification techniques that we talked about. We're just using the resolved object identification techniques that are standard in Atlas. And for this search, we're looking specifically for at least one electron or muon in a hadronic tau, or no electrons and muons and 2 hadronic taus. And 2p tag jets by standard Atlas algorithms. We just look for jet type objects that look like they're b tag jets. We have 3 signal regions here. 2 of them are with an electron or muon, and these are separate depending on what trigger we're using in the Atlas detector. So the trigger is how we decide whether an event, a collision event that occurs in Atlas is interesting enough to record. So one of the criteria we could use is, well, it looks like there's a lepton, an electron or a muon, typically in this case. So that's this signal region. And there are, however, some requirements on momentum of this lepton that are needed to reduce the rate of the trigger so that we don't accept just like way too many events and we can't record them. And so to make up for that, we also use what we call a lepton plus tau trigger. So that is looking at events before we record them and saying, is there something that looks like an electron or muon and something that looks like a tau? And so you can see that's a much lower number of events fit that criteria. And so we can look at objects that have lower momentum. And then for the 2 hadronic case, we have both a single and a di-tau trigger. So we're looking for 1 tau with relatively high momentum or 2 taus with slightly lower momentum. And those are combined together into a single signal region. And what you can see right here is our BDT for the Lept lepton plus tau trigger signal region. So the BDT is trained to try and separate the signal from the background. This signal here is the non-resonant Di-Higgs at the expected limit. And then the background here, it's in log scale, so it's kind of hard to see what's most important, but really the most important one is squished here at the top, is the kind of orangey yellow, which is basically our top and anti-top quark pair background. And then below that is the case of all of the processes that might contribute to cases where we mistake a hadronic jet for a tau. And then below that is eta tau tau, and then below that is lots of other things in standard model hits. Okay, so just a little bit more about our boosted decision tree. And it's trained separately for every signal region, for every mass point, and for every signal type. So there's actually a huge cluster of BDTs, one for each of these variations. It's trained for our signal versus our backgrounds, specifically for the had case, all of the backgrounds, or for the Lept case, just against the top anti-top quark pair backgrounds. And you can see the performance for the had channel here in this plot just here. And if you want to know what variables are included, that's different depending on our 3 signal regions because it was optimized for each particular case. But I have the table right here. We can see all of the variables we're looking at. Most of them are masses of various objects in the event reconstructed, or angular distances between various objects in the event. And then, of course, the missing transverse energy is also sometimes useful. And so you can see what is used. If it's got a check mark, it was used in that channel. If it doesn't, it was not. And then the last thing I wanted to talk a little bit about is data-driven backgrounds. So one way to use a data-driven background is for our Z plus heavy flavor normalization. So what that means is we have Z bosons created, and there are some associated heavy flavor quarks, so like maybe B quarks or C quarks, bottom quarks or drum quarks. that are produced in association with it. And our simulation doesn't do an amazing job of predicting this. So what we do is we look at a control region that is targeting specifically Z boson events where the Z decays to mu mu. So that's completely separate from what signal we're looking for. And then we fit that to data and find out what is the normalization we would expect for this process. And then we use that in our signal region. And then the other source of data-driven backgrounds is this, I mentioned before, jets, hadronic jets that are being misidentified as taus. How do we predict those? Because those come from a variety of different processes. And so I'm going to talk a little bit about what we do for LepHad, because we have kind of a clever data-driven estimation technique that's designed to try and estimate all the different processes that might contribute to this background simultaneously. And we call that the combined fake factor method. So essentially what this is we're splitting up our background into what various different processes we think are going to contribute and just dropping any that are negligible. And we come up with what we call a fake factor, which is a pass over fail factor to convert fail events into pass events for each of these types of processes. And then as a function of the transverse momentum of the tau, what we're going to do is make a total fake factor that is the weighted sum of the different processes that contribute to each bend. And so this is how we're doing this right now. So basically what we took into account is TT bar events and multi-jet events. So the TT bar events tend to be our dominant contribution. The TT bar events would happen where you have like maybe one W decays to an electron or muon in a neutrino, and so we successfully identify that. And then the other top decays into a W and a B, and the W decays to maybe light quarks. And then maybe one of those light quarks happens to pass our tau identification. And then the other source is multi-jet events, where both the electron or muon and the hadronic tau are just jets from some multi-jet event that happens to pass all of our cuts, all of our criterion. And so those are a smaller but not negligible background. So how we do this is we measure these fake factors. What I'm showing right here is where we get our fake factor for the multi-jet events, which I have listed as fake factor QCD because they're QCD processes. And what we do for that is we invert the isolation on the electron or muon. So the isolation means that like when we find it in the detector, there's kind of an area where there's not a lot of energy around it. And if it's isolated, it's more likely to be an electron or muon. Jets tend to have a lot more energy just kind of around them. So if it's not if we don't ask for it to be isolated, then it's more likely to be a jet. And so then we look at whether it passes or fails the tau selection here. And from that, we get a fake factor that we can apply to our taus, where we have our numerator is if we're passing the tau selection, and our denominator is if we're failing the tau selection. Okay. So then the next step is the TT bar fake factor. And for that, we define a TT bar control region, which we want to be enriched in TT bar processes specifically. We subtract what we expect to be true events with true taus, with actual taus in the process, based on simulation. And then we measure again this tau passing divided by tau failing to get our fake factor. And then we use this equation right here, and we weight the fake factor by the fraction of multi-jet events, or 1 minus the fraction of multi-jet events we expect to find for each bin of our tau PT. And that gives us basically not just a normalization, but also a shape for our background that has jets being misidentified as taus in our signal region. So all three of those things go in here into the little fake factor that we apply to data events and get our estimate in our signal region. And then here's the final signal region with the final BDT, with the third BDT that we use. In this case, this is the single lepton trigger for the channel where we have one electron or muon and one hadronic tau. And so here you can see that the jet to tau fakes are quite important, and also that the modeling is very good. The data and the Monte Carlo agree very well in this high background region here in the low part of the BDT. So that's just kind of a taste of the sorts of data-driven background techniques that we use in these sorts of analyses. Okay, so for the results, for our resonant results, in this case, we consider the exclusion in terms of the decay of a scalar or a spin-2 resonance. In practice, whether it's scalar or spin-2 doesn't really seem to have that much of an impact on the kinematics of the signal, so it doesn't really make a very big difference in the result. You can see like kind of a small difference, but not like a lot. So here you can see the scalar case where we assumed a minimal supersymmetric standard model scalar. And then here on the bottom, you can see the spin-2 case where we assumed it was a Randall-Sundrum graviton. And to break it down a little bit here on the bottom left, I included also a plot where you can see the 3 different channels that I talked about. The 2 hadronic tau channel, the lepton plus tau channel, and the single lepton trigger channel. So here, well, okay, sorry, no, the lepad is still combined. So the single lepton trigger and the lepton plus tau trigger are still combined into a single result. But you can see the case where we have an electron or a muon and a hadronic tau, and here in red is the case where we have 2 hadronic taus. So they're kind of pretty comparable sensitivity across the board here, and both contribute to the final combined limit. And unfortunately, as of yet, still no resonance is found. But this was the current best limit that we have, and this is based on 36.1 inverse Fünf-Barn. So we do have 139 inverse Fünf-Barn to analyze. Analysis is underway. Okay, if you're wondering, how does this compare to all of the other Di-Higgs results? So I'm just kind of giving you these in isolation. You're like, okay, maybe these are good, maybe they're not. This is a summary of the results with basically a 36.1 inverse Fünf-Barn of data, mostly. There's a couple of them that only have like 27.5 due to some trigger issues. And you can see all of the different colors. Each different color is a different final state for the Di-Higgs process. And for me, for my group, what we were looking at is the BB tau tau case, which is purple. And you can see it's right here in the middle. So it's a very competitive channel. It's right near 4B and also near BB gamma gamma, which are the other 2 kind of have been powerhouse channels for looking for Di-Higgs. And other channels we've looked at, you can see, is like WW gamma gamma, BBWW, and also 4W here. And the total combination is this black line here. So you can see that all of the channels combine to make a stronger limit. And still not find anything yet. Okay. So then this is all talking about the resonant, but I spent a lot of time introducing the non-resonant case, right? And like looking for the standard model Di-Higgs. So the next question you might have is, how close are we to seeing this standard model Di-Higgs? And so now I have the results for you here. First, remember we have the 2 targets for the non-resonant case, the total production cross-section and the trilinear self-coupling itself. So this is showing the first case, the total production cross-section limit. This is maybe a complicated table here, but the one to look at is the observed column right here, where it is showing in the second entry in each case, where it is showing the cross-section divided by the standard model cross-section. So what this means here is like, okay, if you look at right here, this is the full electron or muon plus hadronic tau channel. And what you're seeing here in the observed is that we have excluded anything that's 23.5 times the standard model cross-section or higher. And you can look at the same thing at the case where you have 2 hadronic taus, and there we have excluded anything that's 16.4 times the standard model cross-section or higher. And when you combine those together, it puts us at 12.7 times the standard model cross-section or higher. And keep in mind that this is still with only like a quarter of the available data. So this is expected to improve once everything is included. Okay, so right now we're at about 13 times the standard model. However, there were all those other channels that I showed you, that we did show you the combination for the resonant case, right? So you might say, well, how do we compare to all the other channels in the non-resonant case? It's a good question. And the answer is pretty well, actually. The BB tau tau channel has been doing very competitive for looking for non-resonant Di-Higgs. So what you can see here on the left-hand side now is for each of the decay modes, the limit on the cross-section divided by the standard model cross-section, basically. So 1 would be the standard model cross-section on this scale. And you can see it goes down to 10 here. So 1 is like over here. We are not at 1 yet, but we are getting closer. So the ones that are further to the left are the stronger channels. The ones that are further to the right are the weaker channels for the moment. And this observed right here is times the standard model cross-section like I showed in the previous plot. And in the total combined limit, you can see now, we have 6.9 times the standard model cross-section. And in terms of individual channels, you can see that BB tau tau in this result was the strongest channel, just by a hair. It's very comparable to the 4B channel, which saw 12.9 times the standard model cross-section. So for the second thing that we were looking for, the value of the trilinear Higgs self-coupling, what we look for is what we call kappa lambda, which is again the measured lambda divided by the standard model lambda. And this is showing what we can exclude here. So this is our theory prediction for the cross-section. So the y-axis here is the cross-section, and the x-axis here is the kappa lambda. So you can see the cross-section gets very, unfortunately, super low for right near the standard model value, and is much higher for as you get the kappa lambda very, very far away from the standard model value. So what you can see here is our limit as a function of kappa lambda, and the allowed area is where this theory curve goes below the combined limit here. So our exclusion is basically that kappa lambda cannot be less than -5 or more than 12 right now. This area right in here is still allowed. So we're slowly narrowing in on the standard model value. Okay, so there was one more thing I wanted to mention, which is kind of like an extension. So Steve mentioned at the beginning that I'm also looking at TTH, at top-associated single Higgs production. And this actually also ties into this search for the trilinear Higgs self-coupling. And the way it does that is that actually at loop level, there is an impact on single Higgs production from the self-coupling itself. And so here are a couple of example diagrams where you have a VBF diagram here that has a trilinear Higgs self-coupling involved. Here you've got a TTH that, again, here's your trilinear Higgs self-coupling. So this is how it would contribute to these processes. And actually, you can get a reasonably big impact on the cross-section, depending on your capital lambda value for a single Higgs. So what this plot is showing you here on the right-hand side is what is the cross-section that you would have relative to the standard model cross-section as a function of your capital lambda value. So you can see where they're crossing over right here. This is 1, so this is the standard model. And then as your kappa lambda gets smaller and into the negative, then your cross-section is getting smaller. And then over here, it's kind of going up and down as your kappa lambda gets bigger. And one kind of outlier you might see in this curve is TTH. So that is why that is something that my group is focusing on as well, because that has a much larger impact from the Higgs self-coupling than some of the other channels. However, they are all useful. And this is just kind of a snapshot of the result that we have with including both Di-Higgs and single Higgs. So one thing to note is that the single Higgs are mostly with the full run-2 data set, and the Di-Higgs are mostly with 36.1 inverse femtobarn. So please don't read anything into the sensitivity too deeply there. But what this is showing is that we can get an improvement. Now there are 2 cases that we can consider here. One, what we've been doing up until now is assuming that everything else is perfectly standard model-like, except for this kappa lambda value. And so that's what this kappa lambda only value is. That's what we've done up until now because we don't have any power to constrain anything but kappa lambda. And you can do that fit, and you can find your observed limit is -2.3 to 10.3. So you can see that's already an improvement over our latest Di-Higgs result by adding in the single Higgs information. Okay. Then what we can also do, though, if we have all our single Higgs information, is we can fit a generic model, which means we allow all of these other couplings to also vary, and we constrain them all simultaneously. So if there was some new physics that's like, say, I don't know, impacting the coupling of the Higgs to the top and the Higgs self-coupling, then that could show up in this generic fit. And because we have both Di-Higgs and single Higgs in the same fit, we can constrain all of these simultaneously. And so that's what you're seeing here, where we get mostly 1 across the board with this fit. And then the kappa lambda, you can see the kappa lambda constraint is a little bit weaker because the fit is more complicated and allows more things to vary. but still, even with just a generic fit where we allow all of these couplings to the Higgs to vary, we get a range of negative 3.7 to 1.5 to 11.5, sorry, that is allowed only. So this really highlights the gains that we can have for collaborating between Di-Higgs and single Higgs teams. All right, so that kind of brings me to my conclusions. So Higgs boson pair production is interesting in the Standard Model, but it also gives us a nice window into new physics. The Di-Higgs community is really active in Atlas, and there's lots of new results all the time. New ideas are quickly progressing. We have a lot of interesting ideas coming up in future analyses, and we're looking forward also to getting more data and many, many more new ideas to apply. So, any questions?
Okay, yeah, no, thank you very much, Allison. We'll just give you the usual round of applause. There we go. All right. Sorry, that was a lot louder than I expected. I'm having all kinds of volume problems on my side today. If you want to ask a question, just type the word speak in the chat window, and we'll go ahead and use that as a speaker queue. And while we're waiting for somebody to type it in, I'm going to use the chair's prerogative and ask a question. Okay. So, you know, you've given us results from Atlas, including combinations of single and double Higgs and all of these channels, but you kept emphasizing that it was only about 36.1 inverse femtobarns of data total, depending on the channel, which you also said was about a quarter of what was collected in run 2. Can you project forward to us what you kind of naively expect the sensitivity to look like absent a discovery by the end, by the time you publish all run 2 data?
Given analysis improvements and the increase in data, I would say we can probably get, we can at least half this in the BB tau tau channel.
Right. So, right, so it's just scaling kind of naively by square root of 4, you'd expect that to come down to between like 6 and 7 somewhere.
Right, yeah. And so I would expect that with analysis improvements, like I didn't really go into all of the things we have planned, but, you know, new machine learning techniques, new boosted techniques, you know, everything we can come up with, I'd expect us to get a little bit lower than that as well. So,
right, yeah.
I would say 6 to 7 is kind of the upper bound of what we could hope for.
Right, if you assume no improvements and people aren't smart and all that stuff, but people are smart, and you've pointed that out, that you do expect improvements beyond just statistical scaling, right?
Yeah, and so then keep in mind that we are going to have all of these other channels that are also going to be seeing improvements. So given that, I think that we are going to be pretty close to the standard model cross-section with the full data set.
So I don't see anyone queuing up to speak yet, so I'll ask a second question, and I'm going to riff off of people who've asked this question of other speakers before during this forum. So let's say you're a graduate student, you're looking to take on a project for the summer or beyond. What are the kinds of things that you would want graduate students to get involved in if they showed up in 3 months and wanted to get active into this program somewhere? So
I would say right now, there's still probably a lot of room in non-resonant Di-Higgs. That's been a major focus for Atlas right now. So it's kind of a hot button right now, but there's still a lot of room for students to get involved. There are signal studies to be done. Maybe if we can find better ways to kind of narrow in on this kappa lambda value. There have been a variety of ideas on how we could better parameterize it for the limit here. I think that could be an area that a student could get involved in. And there are also uncovered channels as well. If you remember my, oh, did I go too far?
Oh, that grid at the beginning?
Yeah. So you can see there's also a lot of uncovered blocks here. So some of these could contribute significantly to the sensitivity of the Di-Higgs case.
Okay. All right, Pavel, go ahead. You had a question or comment. Oh, hang on a second. Yeah, you seem to have an audio compression problem. It's giving you a very high-pitched voice.
You should hear me.
Yeah, there we go.
Yes.
Okay.
Yeah. You were just flashing the slide with the distributions for various values of kappa lambda. I wanted to ask about it.
The
differential distributions for kappa lambda 1.
These?
Yeah, this one. So again, why are there two peaks? So you see that basically, depending on the value of kappa lambda, you can have one or two peaks. So what exactly? Well, perhaps is this related to the two contributions that you were showing?
Yeah, basically. So we have basically separate diagrams contributing to the final state that we simulate separately, and then we add them together with some fractional contribution depending on the kappa lambda value. So you can see here, if this is larger, then you might get a double peak structure, right? Because this one's peaking here and this one's peaking here. Right. So it's really just like the combination between the different contributions.
Okay, and now the other question, this is again a naive question. So, well, you mentioned that you use all these very advanced techniques to search for these very rare events. Mm-hmm. How do you know that you really find a candidate for this very rare process and not the background? So, in other words, how do you validate basically your let's say impression based on this very advanced techniques that for example, you really control the uncertainties in this analysis?
Yeah, I haven't really talked very much about our uncertainties in here because that's kind of gets down into the nitty-gritty of the analysis. But we do have, I don't have a slide for this actually, so I'll just stay here. We have a complex system of uncertainties that we take into account. So there are uncertainties from a variety of different sources. We have uncertainties on the luminosity of the LHC collision, luminosity measurement of the LHC collisions that we're using. We have uncertainties on basically every reconstruction and identification technique that we use as well. And then specifically for like the data-driven methods that we have, there are also associated uncertainties with those that we make sure, like, typically we test those in what we call a validation region, which is expected to be signal depleted but background enhanced. And we make sure that any deviations we would see there are understood and covered by uncertainties as well.
Okay. And then basically the reason you trust your, the results of these searches is because you have a very good description of the control region and whatever deviates in the signal region, then it must be coming from the Higgs signal, right? So.
Right, and so like one of the things that we also refer to as a control region is like the low region here in the VDT, for instance, where it's we have like 10 to the 3 background and 10 to the -1 signal expected, right? So if we have a very good description of the background in that area, then we can expect that it would continue to be well modeled. And we do check this also in validation regions. Specifically, we have looked for the cases where we have like 1 BTAG and 0 BTAG to make sure that the full distribution looks well modeled, where we expect there to be a very small signal contribution.
Okay. And you can also do the same with these new advanced machine learning techniques that you propose.
Yeah, the same.
Okay, thank you.
Yep. And actually, complementary to the question you asked, Pavel, which I think is really the key question in all of this, you've pointed out that there are other final states of this process, BB gamma gamma and the 4B final state. And along with 2B and 2 tau, they're all roughly comparable in sensitivity, assuming that they're probing the same process. So presumably, Allison, if your group or your team saw something in 2B, 2 tau, but the BB gamma gamma and the 4B people didn't see it, you'd probably get suspicious that there's some unmodeled tau background, right?
That's true as well, yeah.
Yeah.
Because, yeah, we would expect to see kind of simultaneously.
Right. So really, looking at several channels help you to be confident that you control all backgrounds in this case.
Yeah, exactly.
Okay.
And if you don't trust Atlas, there's always that other experiment on the other side of the ring, right? So
well, I don't know if you guys talked to them at all, because again, yeah. So clearly, it's a major effort, and the next question is, how are you going to combine it with that experiment and
with CMS?
Yeah.
Yeah, that's, I think, a little bit further down the road, because we need to do our full run to Atlas combination, and then we'll need to talk to CMS. There is a lot of communication with the CMS community, actually. We do have regular workshops where CMS and Atlas come together and talk about published results, of course, and techniques. And there has been a lot of work ongoing to make sure that all of our results are comparable, and that any differences like in sensitivity in various channels is understood.
Right.
So I think when it gets to that point, we'll have the framework at least to communicate with them and make sure we can correlate uncertainties and such where needed.
Very good. Look forward to it, and you still have many years to go. So there will be further improvements on in all these important searches.
I hope so. Yes.
Yeah, I think being forward-looking like that, if we take what 3 or 4 times the data in run 3 that we had roughly in run 2, then this will come down another factor of root 3, assuming no other improvements. You're getting pretty close to the standard model at that point on a single experiment, and then between the experiments, it gets really interesting, perhaps. So. All right, other questions or comments? Oh, Deiana, let me get you unmuted here. Go ahead.
Yeah, hello. I'm actually curious about how different teams are cooperating in terms of fake factor calculation. For example, were any questions raised by CMS group the way you calculate the fake factor?
So I would say many groups use very similar methods, but typically it is derived like per analysis group. So even with an atlas, there has to be a lot of talking and reviewing in between analyses. There was an effort to get kind of like a centralized fake factor estimate for taus that like everyone in atlas can use, but it's extremely complicated because if you slightly change like the kinematic region you're looking at or something, the things can get different. So it's hard to find a one size fits all kind of estimate. And so in principle, the techniques that we use for jet to tau fakes, I think, are pretty common between atlas analyses and CMS analyses as well, with, of course, some differences based on like them using their detector is slightly different than ours.
Okay, thanks.
But yeah, there's a lot of review that goes on in between analysis teams.
Yeah, because it seems like a lot of things are sort of like you choose something, you're making a choice, and then everything is sort of built on it. So I was curious about how people debate over those choices.
Typically within Atlas, I would say in group meetings, yes, there is a lot of discussion about why did you define this control region like this? Why did you define this fake factor like this? And then typically with CMS, the discussion would only be after the publication, and then that would happen in, in the like joint workshops, and people would say, we don't think that your fake method is as robust as it could be or something, and then argument ensues. And hopefully it comes to a more understanding on all sides.
Okay, thank you.
Yeah, I think it's generally true that the discussions, especially about these things, at least with an atlas, are rather passionate. And the day that in an atlas meeting there isn't a deep-seated philosophical disagreement about a fake factor or other kind of scale factor method, I will realize that Atlas has given up. I think Allison would agree that sometimes it painfully slows the process down, but it's well intended, that's for sure. So, any other questions or comments? This has been very lively. Thank you, everybody. All right, I don't see anything else. So Allison, let's go ahead and thank you one more time. And thanks to everybody who participated today. And we'll go ahead and close the event out. So thank you, Allison.
Thank you.
All right. Bye, everyone.